Something unusual just showed up in Ferrari's car at Suzuka. Buried in the official paperwork for the Japanese Grand Prix is a detail that most fans scrolled right past. Ferrari made their front brake ducts smaller on purpose. Not bigger, smaller. So, how does a team chasing Mercedes in the Constructors' Championship gain speed by making a cooling system worse? Nobody in the paddock was paying much attention to brake duct shape heading into the Japanese Grand Prix. The big headlines were about Mercedes stretching their constructors' lead to 31 points, about Red Bull's four-part upgrade package, about whether Hamilton could find more pace in the Ferrari after his first podium in Shanghai. Brake ducts barely show up in the average race weekend preview. They sit deep inside the front wheel, hidden from cameras, ignored by commentators. That was about to change. Every team that brings changed parts to a race weekend must report them to the governing body before the car hits the track. The write-ups are usually dry, technical, and kept as vague as possible. Teams treat these filings like poker hands, showing as little as they can about the thinking behind each change. Ferrari's entry at Suzuka was different. It was surprisingly clear about what the team was doing and why. The first change targets the front corner of the SF26. Ferrari shrank the inboard exit area of the front brake duct. The thinking is spelled out in plain terms. Suzuka's braking load is light enough to support a smaller front brake duct shape, and the trade-off between less brake cooling and better aero tips firmly in favor of speed at this track. That is an unusually open thing to admit in official technical paperwork. Teams almost never explain the thinking behind an upgrade in their official forms. Ferrari basically told every rival team with an internet connection that they were choosing to accept higher brake temperatures because the aero gain was worth the risk. The second change targets the floor body. Ferrari reshaped the front floor stay fairing, a small shape update designed to improve local airflow and recover floor performance. This part was not built just for Suzuka. It was ready earlier and added into the Japanese Grand Prix package because the timing worked. Two updates, both aimed at the front end of the car, both working toward the same aero goal. If that sounds like a small change, keep watching, because what these two updates pull off together is anything but small. To understand why a smaller brake duct exit matters, you need to understand what the front wheel does to the air around a Formula One car. And the answer is, nothing good. The front wheel is the single biggest source of aerodynamic harm on a modern Grand Prix car. As it spins at speeds past 200 kilometers per hour, the tire surface drags air along with it, throwing it outward in every direction. This creates a messy wall of disturbed air that spreads both inboard toward the floor leading edge and outboard into the free air next to the side pod. The tire itself squeezes air where it meets the track surface, creating what engineers call tire squirt, a high-energy jet of rough air that shoots forward and sideways from the contact patch. And sitting right behind the wheel, the hot exhaust pouring out of the brake duct makes the problem even worse. Every bit of extra disturbed air near that front wheel cuts into the total pressure reaching every aero surface behind it. The barge boards, the side pods, the floor, the diffuser, the rear wing. They all suffer when the front wheel wake is messy. This is why modern Formula One brake ducts are not simple tubes that push cool air onto hot brakes. They are complex layered units with stacked airflow channels inside the brake drum housing. Some of those channels soak up heat from the carbon brake discs and push it out through set exit spots on the end fence of the duct. Others serve no cooling purpose at all. They exist only to control the shape and behavior of the messy wake created by wheel and tire spin. Teams spend thousands of hours in computer airflow testing and wind tunnel runs to fine-tune these internal channel shapes, because the stakes are huge. The spread of tire squirt and the lower wheel wake grows right into the path of the floor leading edge on the 2026 car layout. That spread cuts total pressure under the car and limits how much downforce the floor can make. Controlling that spread has been, and will continue to be, one of the most important goals when working on the front end of any Grand Prix car. Ferrari's answer is simple in concept. Shrink the exit area, shrink the amount of hot air dumped into the wake. With less heated exhaust leaving the brake housing, the wake behind the front wheel becomes tighter and more stable. Higher quality airflow with greater total pressure reaches the floor leading edge. The floor seals better against the track surface, and the car makes more downforce. The reshaped floor stay fairing then takes advantage of this cleaner flow, cleaning up the local airflow to pull more performance from the underfloor. The two parts work as a system. The brake duct cleans up the air, the floor fairing captures it. Neither part would deliver its full gain without the other. But this raises a clear question that goes beyond Ferrari. If smaller brake ducts create better aero, why doesn't every team run the smallest possible duct at every single race? The answer is heat. Carbon brake discs on a Formula One car work inside a temperature window between roughly 400 and 1000 degrees Celsius. Below that range, the brake pad material glazes over and braking performance falls apart. The driver pushes the pedal, and the car simply does not slow down the way it should. Above that range, the disc starts to break down, risking total failure at the worst possible moment. Brake duct sizing is really a heat control problem. Engineers work out exactly how much airflow the brakes need to stay inside that working window over a full race distance, factoring in air temperature, tire wear, fuel load changes, and the specific braking profile of each track. They size the duct to match, making the duct smaller cuts cooling. At tracks with heavy braking, like Monaco or Singapore, where drivers spend over 20% of each lap on the brakes, that would be a death sentence. The brakes would overheat, the pad material would fail, and the car would sail straight off the road at the next heavy braking zone. Suzuka is the exception that proves the rule. Suzuka rates 1 out of 5 on the standard brake difficulty scale, the lowest possible rating on the entire calendar, tied only with Silverstone. The numbers explain why. Brakes are used on just 9 of the track's 18 turns. 3 of those braking zones are shorter than 50 meters. Drivers spend fewer than 12 seconds per lap pressing the brake pedal, which works out to roughly 13% of the lap. Average deceleration is just 3.3 g, the lowest of any track Formula One visits all year. For contrast, a street circuit like Singapore demands more than 100 metric tons of total brake pedal force over a race distance, roughly double Suzuka's figure. Suzuka's nature is shaped by its flowing high-speed sections. The famous S-curves through turns 3 to 7 are taken nearly flat out, with the car loaded sideways at forces past 4G, but with almost no braking. The long sweeping left of Spoon demands guts and precision, but not heavy brake input. And 130 is one of the most famous flat-out corners in all of motorsport. These sections load the car laterally, not longitudinally. Only the chicane between turns 16 and 18, where cars brake from over 300 kilometers per hour, and the hairpin at turn 11 count as truly heavy braking zones. Under the 2026 hybrid rules, the picture is even more extreme. The 350 kilowatts motor generator unit handles a large share of deceleration through energy recovery, meaning drivers barely touch the brakes through the S-curves at all.